Okay. So, and I'm going to end this lecture soon. Just a few more things to discuss. So I want to talk very briefly about entropy as a state function. So let me collect myself here. Okay. So, and what I'm showing you here is what we call a path. Okay. And so entropy along this path. So we remember that entropy is dq reversible divided by temperature, okay? And as it turns out, in proving this picture right here, if we were to integrate this picture, and I'm going to show you if we were to do the path integral, and the path integral means integrate along this closed loop path, okay? Then we would get 0, which is just basically another way of saying if we integrated and started here and made it to the final state and then came back all the way around here, we would just have ended up where we started, and there would have been no change in entropy, okay? Or in other words, the entropy of the final state would have been equal to the entropy of the initial state. Now the path, the amount of heat conducted might not be 0, right? Because we know Q is a path function. However, we do recognize in the state function, I'll just write delta S, that we're only interested in the final entropy and in the initial entropy. Okay? So, and then of course, we can also conclude another bigger picture from this idea here is, and I have another definition here, and I'm not, another derivation, and I'm not going to go through it because we've kind of already proven that before. So I'll just do it briefly, but S total equals 0 for all reversible processes, okay? So that's kind of the conclusion I wanted to come to by doing a derivation. But I think more importantly, I would rather you just know conceptually delta S total equals 0 for all reversible processes. And the example of this with isothermal expansion comes from the fact that in isothermal expansion, delta T, that says delta F, delta T equals 0, delta U equals 0, negative Q equals positive W, okay? And if we keep going with this, we know work reversible, instead of deriving it, I'm just going to throw the equations up. Negative nRT, natural log over VF over VI. So then as a result, Q reversible has to be positive nRT, natural log VF over VI. Okay. We recognize that delta S surroundings equals Q of the surroundings divided by temperature, which is the same thing as saying negative Q reversible divided by temperature. So instead of saying reversible, I'll say system, just to not confuse that. System, okay? Well, the Q of the system is right up here, okay? Which is just going to be divide this by T, so that's going to be negative nR natural log VF over VI. So that's our delta S for the surroundings. What's the delta S of the system? Well, the delta S of the system is just going to be equal and opposite of that because it's reversible. So delta S total is just nR natural log of VF over VI, but the surroundings is negative nR natural log of VF over VI, which equals 0. So I guess I still ended up doing that kind of short, very short derivation. But conceptually speaking, hopefully it makes good sense that delta S total has to be 0 for all reversible processes because you basically start and end in the same place. Delta S total is greater than 0 for all irreversible processes. Okay? Sorry, my handwriting is kind of going to shit today. Normally does on most days. Okay, so great. So that's where I'm going to end it for today. So just kind of introducing entropy. We're going to get more into the meat of this as we progress. I will see you later, folks.